don't have them graded yet. I'll grade them this afternoon. I thought a lot of people would come today just to see what the grade is. Still, we had a typical Friday, very few people. So we get to move on now to something besides kinetics. I did kind of start equilibrium, but I'm going to start again as if I didn't. Equilibrium. For an example, if we write this reaction. And the double arrow means, I think I've said this before, is typically you would say, here I put in this reactant, it reacts, and you get this as a product. In which case I would have just one arrow pointing here. And after the reaction, there'd be none of this, and you'd have only products. The equilibrium is saying that if you put this by itself into a reaction chamber, and since these are gases, I'll say, you seal it up, that's a gas, and you seal it up. Some of this will become this, but there will be a good bit of this still left over. So it's sort of like, if I start with only NH3, equilibrating, going back and forth. Okay. Let me say, so here's the reaction I'm talking about. And this, think of that like a bar graph indicating how much NH3 is there. And let's say there's none of these there. You've got this, you seal it up in a reaction chamber. What happens is, this will start to go down. You'll get a little bit of this and this. And so there's kind of this force going, okay, this arrow is forcing us this way. Once you get a little bit of this, there's a tiny force pushing back a little bit. But it's not enough to stop the force going this way. So this goes down a little more. These go up a little more. This one's force increases a little bit more. And this one goes down a little more. These go up a little more. And then it's sort of like the force on either side becomes equal, and then it just stops. And you could have very little of this and a lot of this at equilibrium, or you could have a very little bit of this and a lot of this at equilibrium. But picture it kind of somewhere not in those extremes, just for something to picture. But that's what equilibrium is. There's a lot of important reactions that do this, so it's a big topic. And for reasons that your intuition won't really be able to see into, there is a particular numerical value that goes along with an equilibrium that helps us state what the proportion of products and reactants are. And you would write it, for instance, for this one, you would write concentration of N2 times the concentration of H2. So that's the products. And that 3 I'm going to put up here as a power. And then the reactants go down here. So reactants always go in the numerator. So it's always products over reactants. And this 2 will be here. And that numerical value, wherever it is, even if it's away from equilibrium, we call this the reaction quotient. Your book uses a C to indicate we're doing the reaction quotient as a function of concentrations. There's another way to do this with partial pressures when it's a gas, but I'll do that in another day. So this numerical value called the reaction quotient. And let me get just a number line going here, and let's say we start this reaction and we're not necessarily at equilibrium. Let me just move these for now. We're not at equilibrium. So the reaction is still going on, approaching equilibrium. And let's say, whatever these concentrations are, we get a numerical value for Q, and let's say it's right here. So let's say that's Q1. Time goes on a little more. And let's say, for this case, I want this to increase. So let's say this is decreasing while the numerator is increasing. That is, we're in a process of going this direction and building up the products. So this is going down, and the numerator is going up. That's going to make QC go up, so I'm going to make QC, say that's Q2. Time goes on, this continues, this gets smaller, these get bigger, Q3, and then we get to this special point where it stops. This stops changing, those stop changing, it just stops. If you track it over time, what I've got going on here, and this was Q, you would see, you calculate it and you take another snapshot and calculate it and calculate it and calculate it, and you would see it do this, and eventually it would level out and just stay at one particular level. This level, that special spot, spot is what we call K, the reaction constant. I should have said equilibrium constant. So it's only at that special point that we call the solution to this equation K. It's called Q outside of that. That's just nomenclature. Okay. And I could do this the other way, where if I had most of this, so that this was huge and this was very small, then I'd have a very, very large Q, call that Q1, and then as time would go on, this would get a little bigger while these get smaller. That is, some of these react and start becoming this, and then we would be starting up here and coming down equilibrium, and then it just stays here forever. As long as nobody comes and messes with anything, it will just sit there and stay at that particular ratio of products to reactants indefinitely until somebody comes and disturbs it. Sometimes that happens very fast, sometimes it takes a long time to get to equilibrium, but once it gets there, it stays there. That's the concept of equilibrium. You with me? All right. So yeah, if you let time go on, this Q, you'll eventually get to K and you'll stay there. So this is what I mean by this. That's K. That's fine. Okay. So, if you had concentrations at equilibrium, you could calculate the equilibrium constant, but that isn't real typical for problems to work on. So let me do this. I guess I can do this up here. All right, let's say we're at equilibrium, right here at K. So this is where Q equals K, right there, and it's Q anywhere else. So I'll just keep this number line. Say that's K. All right, let's say you're at equilibrium and you're just sitting there. So let me do the bar chart here. So we've got that, and let's say it's something like that per amounts. So there's my bar chart showing how much is there of each one. Let's say at some instance in time, you squirt a little more of NH3 in there. You've increased the concentration of NH3 by introducing some extra NH3. You just squirt some through a little hole and you close the hole. At that very instant, suddenly this has gone up. If this goes up a little bit, or think about it as a lot, just to be clear, but if the denominator increases some, what is that going to do to the value here? Huh? It gets smaller. The answer to this equation will be smaller right after you squirt some extra NH3 in there. So there's my extra NH3, the black there. At that instant, you've made this calculation bump up to here. So now you've got a Q up here. But over time, the laws of physics is going to draw this back down here. That is, if suddenly you have a lot of this, then what's going to happen is okay, so this goes up. For this to come back down this way, what has to happen is for this, suddenly made that big. No, that got smaller, right? So if you suddenly made this bigger, you made your calculation down here. And then it's going to force its way back up to K, meaning if you suddenly made this, the answer to this smaller by making this big, this is going to start to shrink while this goes up, and then you'll walk your way all the way back up to K. But at that first, here's what happens. At that first instant, you get that. And over time, this will go down. So let's call that Q1 as soon as we did that. Q1. A little time goes by. And some of this NH3 starts becoming product. So the amount of NH3 starts to go down. I'll call that Q2. So as this starts to go down from here down to here, this one goes up a little bit. You get a little more N2, and you get a little more H2. So this will go up a little bit. And then we just do one more. Let's say that's Q2. And then when you finally get back to K, where this lands is, let's say this is where we get back to K. There's still a little extra of NH3 than there was to begin with. This green line here is what there was to begin with. And then I added this, and I'm just saying you still have that, plus a tiny amount of this extra you put in. That's what you'll have when you get back to K. And these, I'll just make the black part a little longer. So this was Q1, Q2, and K. And by the time it's gotten back to K, you're back to here. So you get questions like this. If I do this, if I add a little bit of reactant while it's in equilibrium, I kick it off of equilibrium, it comes back to equilibrium, and at that point the question is, how has that affected the amounts of the things that are there? The NH3 has increased a little bit once it goes back to K, because there's still a little bit here that you added. You see that little tick that I've got there? So there's a little bit more of this, and of course, you increase the amount of N2 and increase the amount of H2 once you get back to K. You follow that? The simple way, when we say, we call this Le Chatelier's principle. If I add some of this, it flows away from it. And this works if I go the other way. If I add one of these, it'll flow that way. So let me do it the other way. Here's what happened. I added some reactant, and when it came back to equilibrium, I had just a little bit more reactant than I had before. You don't have this much more because some of it reacts, but you still end up with a little more than you had at the beginning. And then, of course, you end up with more of this and more of this because the reaction flows that way. But it comes back to equilibrium. But let's do it the other way. Let's see. Should I do this? No, let me not do that yet. The summary, but I increased this reactant, and then when it came back to equilibrium, I had a little bit more of this, and more of this, and more of this. I should have done this with 2 reactants. Let me do it as the product. I'll show the point I'm trying to make. What if we're at equilibrium, we're at K, so the answer to this equation equals K on this number line. Let's say we have those as starting amounts, and let's say that much of that. Okay, we're sitting there at equilibrium, and you can sort of see the proportions of what's there. All right, and then I suddenly, let's say I add a bunch of this, kicking it off of equilibrium. If I increase the amount of a reactant, amount of a product, that's up here in the numerator. So now I'm making the numerator bigger. So what does that do to K? Does make it bigger. So the answer to this equation will go higher now. So let's say we're up here, and I'll call that Q1. So I'll say right at Q1. I should have had one more here that said K. But, sorry. But okay. So at that instant, you're here, and now the laws of physics will take over, and it's going to work its way back to equilibrium. That big bump you gave the numerator is going to start shrinking while the denominator starts growing, meaning it's going this way. You're getting less of this and more of this. So let's say Q2 will have, that's the original amount. That's the original amount of that. That's the original amount of that. So as it flows this way, get at Q2, you'll have a little more of this, and over here, you're actually going to have a little less of this. This is where I want one more color. Maybe. This one's green too. I don't know if it'll show up or not. You can see that. Let me exaggerate. Here, that little bit right there. That little bit represents this going down. That's how much of this is lost compared to here. So this is a loss. Oh, I suppose I don't have to put that here. Let's just do that. Q2. This has gone down, and this will go down some too. And then this will increase a little bit. So starting amount, then you inject some of this. So the next time period at Q2, this will have increased a little, this will have decreased a little, and this will have decreased a little at Q2. So it's on its way back to equilibrium. All right. And then we'll do initial amount, initial amount, initial amount, 3. This one will have increased a little more. This one will have decreased a little more. There's still some of that that you added just a little bit. And this one will have decreased some more. So what happened in the process of adding some N2, once it gets back to equilibrium, oh, I should call this K. Let's say that's back to K in the third one. The third time snapshot, we made it all the way back down to K. So what happened once you got back to equilibrium? Well, compared to the original amount, now there's more of this, so that increased. There is a tiny bit, just by a little bit, that increased. And this one decreased. You follow that logic? So it was at equilibrium. I squirted one of these products in, and it shifted this way, so we ended up with a little more of this when we were back to equilibrium, a little more of this when we were back to equilibrium, and less of this when we were back to equilibrium. That's one of the types of questions you get about equilibrium. If I add some of this, what does it do? And typically, you can say it like this. I would say, if I add some of this, it flows that way to get back to equilibrium. If I add something over here, it flows that way to go back to equilibrium. That's the quick, simple way to put it. And then there is one more twist. You can talk about removing some. So let's do that. So we start with initial amount. Remove over there. So let's say this is your initial amounts at equilibrium. So how does that work? Here. This one. Let's say that's our starting point. Okay. Now the black will represent removing the sum. So that's our initial amount. And what I do is I remove. I wish I had one color. Oh, I really need it. Let me see if there's one back here. Use your blue. So the blue now, so let's say I'm going to remove some of this N2. So I'm somehow able to selectively grab the N2, suck some of them out of the chamber, and that's what this represents. This represents, the blue represents what's been removed. So if I remove that, and that's where we are, right at the instant, what I've done is make the top smaller. So if this gets smaller, that's going to kick us down here. I'll call that Q1. Right at the instant that I've squirted more, no, that I've removed some. Remove some. All right, so of course, this is going to work its way back up this way. You have a Q2 somewhere in the middle. The Q2 would look like, if I remove this, then it flows towards what you remove. It's sort of like anything you put in, it flows away. Anything you take out, it flows towards. So if I take this out, it's going to flow this way. So this will go down a little bit. So the blue represents what's missing. So that will go down a little bit. If I remove this, it flows this way. So I'll lose a little bit of this for Q2. And I will actually gain some more of this. Do I make that blue? No. I'll just do this. put in. So we have more of this, and this will go up too. This one will increase. So if I suddenly decrease the top, then the top's going to increase while the bottom decreases to get us back up here to K. So this is Q2. That decreased, this increased, and this one increased. And then when we get back to K, I guess I'll finish it. This has increased a good bit. Not sure my blue really means anything. Let's say this one ends up way up there. This one ends up here. Put blue here. This one ends up like that. And this is where we're back to K. Q2, K, Q2, K. And the point is, if I remove some of this, I'm going to end up with more of this, I should say, increase. This one increase. So if I remove this, no. I remove this, this is what happens. So this is what I've removed, and then some of it starts coming back. And replacing some of what I removed. And then by the time we get back to K, it's almost replaced everything that I've removed, but there's still a little bit missing. So if I remove some of this, I still end up, even after we flow back this way, having removed this, I get back, I still end up having just a little bit less than I started with. If I did that well. That little blue tick right there, this still did actually decrease by a little bit. But this one decreased. Yeah, this one increased. This one decreased. Okay, remove this, we flow this way. So we get less and less of this till we get back to K. We removed this much of this. I just want a picture in your head here. Let me try to draw this one more time. Remove that. All right, this is what I removed. And then this is what I'm trying to say. Some of what I removed comes back, and then a little more of what I removed comes back, but it never quite gets back to where it was. So you still end up with a little bit of a decrease if I remove this. But once I remove this and it flows this way, this one increases and this one decreases. So if you add something, when it gets back to equilibrium, you still have a little more extra there. If you decrease something, by the time you get back to equilibrium, it goes up, but it didn't quite get back up to what it originally was. So this decreased by a little bit. This one increased by a good bit. This one decreased by a good bit. To get us back to equilibrium. You follow that? So equilibrium. Equilibrium. And then we'll say I want to say shift equilibrium. I'll just say one way to screw with the equilibrium. Change concentrations, you can screw with the equilibrium. It does come back to the original K that it was. Okay. Put cartooning explanations on here to say, this whole time when I was doing all of this, K never changed. Q changed, but whatever the numerical value of K was, and assume everything we were doing over here was constant temperature, and I'll also say constant pressure, because that's where I'm going over here. K, whatever the numerical value of K was, it never changed. We were able to kick it off equilibrium, and we get a Q that was different. But then it would work its way back to that very spot, the actual numerical value of K. When you change the temperature, and now what? I'm going to have to use a different equation just to be sure. No, here it is. If I told you this, I'm going to add this a little bit of information. Delta H of this reaction is, I'm going to put a positive sign just to indicate, just to emphasize, 92 kilojoules per mole. So that didn't mean anything for us, what I was saying before here, but let me just say, okay, that's the delta H of the reaction. That's this, if you wanted it in a diagram. Reactants, it's positive. Products, it's this difference, is the delta H. Another way of saying this is this was endothermic, right? Because we ended up with more energy in the atoms, molecules, than we started with. So that's what the plus means. We ended up at a higher energy, so that's plus delta H. So there's an extra piece of information. At one particular temperature, K doesn't change. But let me show you what you do. Let's say, when it's endothermic, it's like heat is a reactant. When it's exothermic, it's like heat is this is kind of a mnemonic, really. But think of it like this. If I do a reaction, and heat comes out and heats up and I can feel the heat coming from it, it's kind of like those two things that I formed, those are products of the reaction, but so is heat. You see what I'm saying? Of these two, that's the more, I think is the more intuitive. If it's exothermic, that means heat came out. That means if you were standing there when you did the reaction and you felt the heat, you go, one of the products, one of the things I produced was heat. Exothermic, when you feel heat coming from. That's the one I think is intuitive. Of course, if you can get the intuitive one, then it's just the flip side. Endothermic is like heat was an ingredient that was needed to make the reaction go. You know what I'm saying? That's not always true. That's not really the activation energy. But what I would say is, this one is endothermic. So think of this. Heat is now one of the reactants. And then the rest is simple. It's just like Chatelier's principle. If you raise the temperature, that's like putting heat in, and that'll make it shift this way. If I reduce the temperature, it's like taking the heat out, and then it will shift this way. But what I'm saying in the shift is you actually change K. K is at a different point. If this was K before and at a low temperature, okay, so let's see what happens. If I increase this, and we're shifting that way, that means the product is getting bigger and this is getting smaller. That means this is getting bigger and this is getting smaller. What I'm saying is, the new K, and that's why I said this, you change K now when you change the temperature. The new K for a higher temperature for this reaction would be up here. And if you did it colder, your new K is going to come down here. You'll have a new equilibrium point. See what I'm saying? Okay. And do I have one that's, you end up with the opposite thing, of course. You have one that's negative. So this one, 203, 302, and that one's delta H is 0.5 kilojoules. This one's calculation would be O2 to the third power, 3 second power. So that would be the equation for this one. Products over reactants. And this time, since 285 joules came out, delta H, that's like heat is a product. And now you get the opposite effect. At a higher temperature, you put temperature in, you shift this way. That's like this getting bigger and this getting smaller. So this one, high temperature, I'm going to use your blue. Pretend I did that in blue. This one, higher temperature, it goes this way, so you get more reactant. So this goes up, this goes down, so you get smaller. I'll put tape up here. And of course it goes the other way. You remove heat, it'll flow this way, but I don't really mean it flows, it's just the new equilibrium is there. It will flow. If you start at a low temperature and you slowly raise the heat, you will slowly go this way. You go a little more, and a little more, and a little more, and then when you stop heating it up, it's at its new equilibrium point. It's at its new lower K after you heat it up. So the effective temperature actually changes K. Change the pressure, change K. In these cases, we actually change the K. I should say, for gas phase reactions. And this one you pay attention to. This one you pay attention to how many moles of gas on each side. We can use this one, or erase the blue one. And we don't really need to pay attention to this for this discussion. Okay, so think about it like this. If I said, how many moles of gas is this showing on this side? and I really mean relative. But let's just say this means 2 moles of gas. So there's NH3 and another NH3. So let's say that represents 2 moles of gas. This represents 1 mole of gas. And I say gas because it's got a G there. G, G, G. Let's say that's 1 mole of gas, and this represents 3 moles of gas. And go, okay, all the moles of gas on this side, there's 2 moles of gas. All the moles of gas on this side, there's 4 moles. You see that? You with me? Okay. Now think about this. What is this going to want to do if I increase the pressure, if I force some pressure down on this system? It's just sitting there in a vessel, and let's say I got like a piston, and I can just push the piston down. 2 ways to say it is I suddenly decrease the volume, but you can also say increase the pressure. Your book says decrease the volume, but it's the same thing as increasing the temperature. I'm going to say increase the, same thing as increasing the pressure. I'm just going to say increasing pressure. But really the only way you can increase the pressure without pumping more gas in there is to decrease the volume. Let's say the pressure goes up. What's the preference going to be for this system? Which way is it going to want to shift? It's going to want to compress. So what will happen is, there's 4 moles over here, there's only 2 here. You can get that gas to compress in a smaller space, less gas molecules, if it'll flow that way. So if you increase the pressure, it'll flow that way, towards the side with lower numbers of. And the other way around, if you decrease the pressure, increase the volume a little bit with the plunger. Now it's got a little more freedom of space, so it'll expand out by shifting this way. You follow that? So you think about how many moles of gas when it comes to pressure change. And that is a shift in K just as well. So let's say I increase the pressure. It's going to shift to this way. It's going to increase the NH3. Increase this while decrease this. Your new K, high pressure, your new K will be down here. If there's more moles on this side than there are on this side. And you decrease the pressure, your new K, low pressure, there's your new K. And the high and the low here will swap if I have a reaction that has more moles of gas here and less moles of gas here. It just goes the opposite way. So you have to look at the reaction and decide which one it is. More gases on the left, or less gases on the left and more on the right, or more on the right, less on the left, and that'll decide which way it shifts. You good? Very conceptual, not a lot to calculate here. There are some calculations in this chapter, but we'll keep it light for a Friday. I will get some of these on D2L. I still haven't. There's a different reaction. This one. It's an equilibrium. So the double arrow tells you it's an equilibrium. These do happen to all be gases. Gas, gas. All right. Delta H here is positive 181 kilojoules. Okay. What's the effect of increasing temperature? Which way does K shift? Up or down? Increased temperature. Does K go up or does K go down? The new equilibrium will be higher or lower? Higher. All right, so think it through. If I had to put this in, it's like an ingredient. So heat is over here. Increased temperature, it shifts that way, so NO goes up. Let me, NO, 2 there. All right, so increased temperature, shift this way, NO goes up while this goes down, so K will go up. K at a higher temp will be higher than the original K. Numerically, it'll just be a higher number. If I decrease the temperature, I'm removing heat, then it's going to shift this way, and then it does just the opposite. It goes down. All right, let me ask you this. What's the effect of increasing pressure? Huh? Well, okay, so how many moles of gas are on each side if we do it the way I did it before? There's 2 moles here, so there's the invisible one for these, so there's 2 moles here. 2 moles of gas. And how many moles of gas over here? 2. So what do you think happens when we change pressure? It doesn't affect it. So if you have the same number of moles of gas on either side, it doesn't affect it. It's just unaffected. So K will stay right where it was for this particular one because it had the same number of moles of gas on either side.
What happens if there's like different moles, like mole values, and you increase the pressure?
If these are different, it's like the first example I did, but let me find another one. Here, let me do this one. Here's a reaction that you can do. Sealed in a chamber. Calcium oxide, that's a solid. With some CO2 sealed in a chamber, and you get an equilibrium. So some of the CO2 gas will react with the calcium oxide and make calcium carbonate. All right, what would be the effect of increasing pressure here? Well, how many moles of gas are over here? Is it balanced? Okay, there's an invisible one there, an invisible one there, and an invisible one there. That's a solid, that's a gas, and that's a solid. So how many moles of gas over here? You really just have 1 mole of gas. How many moles over here of gas? 0 moles. So since they're different, now pressure will affect it. If you increase the pressure, it'll want to shift over here to where there's no moles of gas. And if you decrease the pressure, it will make it shift this way. And it does K accordingly. This one's formula will be, it's always products on the top. Just by convention, we do it that way. There's no coefficients, so there's not going to be anything on these. Concentration of CaO and CO2. So that's how you calculate the reaction quotient. So increased pressure, it's going to shift this way to get more of this. So at a higher pressure, this one's K will be higher than it was at the lower pressure. And if you lower the pressure, it's just the opposite. Lower the pressure, that gives it freedom to expand a bit. So these get bigger, this gets smaller, so K will be lower. You good with that? Choose to picture change. That's the one I've got. I guess I've used all my examples. There's one I haven't used. That one's 95 kilojoules. It's balanced, so there's no coefficients. The product goes on top. So this would be the equation. That'll give us our reaction quotient based on concentration. And of course it equals K at equilibrium. I need to do this. Okay. And they are all gases. And in case you're wondering, this is H2 looks like that. And this is hydrazine. Anyway, in case you wonder. Okay, they're all gases. All right, if I increase pressure, which way is it going to shift? Got 2 moles of gas here and 1 mole of gas here. If I increase pressure, it's going to want to compress to where there's 1 mole sign. There's 2 moles of gas here and 1 mole of gas there. Yes. So it's expanded more over here. So if you increase the pressure on it, it's going to want to squeeze into the smaller space. So it'll shift that way. N2H4 goes up. This goes down. That means we're going to end up at a higher K. So the K at a higher pressure is going to be higher than the lower pressure. And of course, the other way around. To lighten up the pressure, then it can expand. Then it will go this way. And then this is growing and this is shrinking. And so this is K at low pressure. All right, and is that 95? Yep, that's positive 95. So where do I put the heat? If it's positive, it's like I put heat in. If it's negative, that's when you feel heat coming out. So when it's negative, you feel heat coming out, it's like a product, so the heat goes on the right side like a product. When it's positive, that means I put heat in as if it was an ingredient, reactant. See what I'm saying? That's how that mnemonic works. So I want to put the heat over here. Increase the temperature, it shifts that way, which makes this bigger and these smaller. This bigger and these smaller. So higher temperature somewhere up here. I don't know if it's above or below that, but. And if I make it colder, I remove heat, I shift it this way. That means this is getting bigger and that's getting smaller. That's getting bigger, that's getting smaller. So that'll be K below temp down here. So up here when we were playing with concentrations, we would temporarily shift away from equilibrium and then come back to equilibrium, and then you would answer whether you had more or less of whatever different stuff is there. When it came to changing temperature and pressure, we actually shifted where the equilibrium point was. So that's a distinction to know. And if I told you something to practice, because I don't have these on D2L yet, I will ask questions like this on the test. But if you wanted something just to look at the end of the chapter. Look at, do it in order. Number 17. In fact, it's probably these that are going to turn into questions on D2L somehow. So if you want to sort of practice what we did today, since there's nothing on D2L yet, you can practice now. I think I'll just keep it at that for today. We'll do the other pressure equilibrium stuff next time. You guys okay? All right, I'm going to get your stuff graded this afternoon.